आज हमारा ये फर्स्ट लेक्चर है मैथमेटिकल टेक्निक से। इससे पहले बिफोर मिड टर्म डॉक्टर हुमायूं के साथ आपका इंटरेक्शन रहा है, और उन्होंने कुछ कंटेंट जो थे वो कवर कर लिए थे। जो रिमेनिंग कंटेंट थे उसका मैंने लास्ट इंटरेक्शन में आपसे प्लान शेयर कर लिया था। वो प्लान ये आपको शो किया हुआ है। तो इसमें जो आज की डिस्कशन है, आज बेसिकली हम जो अलजेब्रिक इक्वेशंस हैं उसके बारे में हम थोड़ा करेंगे इंटरेक्शन। तो एक लेक्चर में शायद ये कंप्लीट नहीं हो पाएगा एज फार एज आई कुड रीच आउट, क्योंकि अलजेब्रिक इक्वेशन बेसिकली डिफरेंशियल इक्वेशन स्टडी करने से पहले अलजेब्रिक इक्वेशन को प्रॉपर्ली अंडरस्टैंड करना और इसके जो सॉल्यूशन एल्गोरिथम्स हैं उस पे ग्रिप होना, दिस इज वेरी इंपॉर्टेंट, especially with the introduction of different schemes, for example जो finite different scheme है, उसके साथ क्योंकि हायर ऑर्डर डिफरेंशियल इक्वेशंस को रिड्यूस कर लेते हैं आप टिल द लेवल ऑफ algebraic इक्वेशन एंड स्पेसिफिकली फॉर अ सिस्टम ऑफ लीनियर algebraic इक्वेशंस। सो द सॉल्यूशन एट द एंड जो आप ले रहे होते हैं, दैट्स ऑफ द algebraic equations. So this is important to have a firm grip on the system of equations. So uh, जो पार्टली जो लेक्चर ये टॉपिक है ये आज हम कवर कर लेंगे, और जो रिमेनिंग कुछ टेक्निक्स हैं जो कि आज हम कंप्लीट नहीं कर पाएंगे, सो आई टेक सम टाइम इन द फर्स्ट लेक्चर ऑफ द नेक्स्ट वीक। तो फिर उसके बाद फाइनाइट डिफरेंस सेकंड वीक का वो स्टार्ट कर लेंगे। So, algebraic equation, it's not a new concept for you at a master's level. ये basically वही basics हैं जो कि elementary school level से चलती आ रही हैं कि algebraic equation mathematics में एक ऐसी equation है जिसको आप p equal 0 के तौर पर represent कर सकते हैं, and where p is a function or a polynomial with certain coefficients. और जो दूसरी साइड पे अक्सर होता है कि वो इन इट्स ओरिजिनल फॉर्म इट्स नॉट जीरो, रादर इट्स अ कांस्टेंट वैल्यू, और वो कांस्टेंट वैल्यू आप इक्वेशन की दूसरी साइड पे लेके रिप्लेस कर सकते हैं। सो इन स्पिरिट, so polynomial that can be represented as a polynomial equal to zero, that's algebraic equation. That's a very simple concept of algebraic equation and has been there since our elementary school. अब ये कि इस अलजेब्रिक इक्वेशन को कुछ इसकी क्लासिफिकेशन है, अगर उस क्लासिफिकेशन के साथ से डील करेंगे देन इट मेक इट इजियर टू सॉल्व द सिस्टम। और वो क्लासिफिकेशन पॉलिनोमियल्स की या अलजेब्रिक इक्वेशंस की दो तरह से नॉर्मली करते हैं। वन इज विद द नंबर ऑफ टर्म्स इन्वॉल्व्ड इन द इक्वेशन, and other is the degree of the polynomial. So these are two basic parameters for the classification of polynomials. So number of terms के साथ either it can be with a single term like 6 equals 0, no sorry 6 just a single term, or 4x cube equal to 0, or something like that. That only involves one term. That's a monomial. And similarly, we can have with the two terms or three terms or more than three terms or any number of terms. So in general, whenever we talk about the polynomials, it can include even a single term, two terms or three terms or multiple terms. So in general, all are polynomials. But sometimes it's convenient to us to describe it as a monomial or binomial or trinomial. This is just a categorization. Otherwise, all these are polynomials. But the more important classification is based on the degree of the polynomial. And if the degree of polynomial is in fact the power of the variable. For example, on the left side, if the variable is x, x1, x2, or xn, whatever this x is raised to the power, that's so it can be of 0th degree. If it's a 0th degree, then x bar 0 will be 1. So we only will have a coefficient value. Then if it's 1, that's a linear polynomial, or similarly it can be quadratic or cubic polynomials, or polynomials if the degree is more than 3. So in fact, the solution techniques are more relevant when we talk about the degree of the polynomials, and the complexity of the solution increases with the degree of polynomials. It's relatively easier to solve linear linear equations or linear polynomials compared to quadratic or cubic polynomials. At the end, it depends on the technique that is applied for the solution, and at the same time the complexity of the solution that refers to ultimately the cost of computation. And for practical purposes, rather than having only one polynomial, we usually have a set of polynomials or system of polynomials that we normally face our engineering applications. So it's very common for us to face linear polynomials or linear algebraic equations, and specifically when there are multiple linear algebraic equations, and we are required to solve that system. So this is what the background of the algebraic equation is, and we are supposed to go through the solution techniques by which we can solve any set of uh, polynomials. And for today, we are more concerned about the linear systems, especially in the coming weeks when we will be talking about the uh, differential equations. Then our focus will be somehow to reduce the differential equation into non-differential all the algebraic equations, and at the end solve the algebraic equations. So that's why we are more concerned about the solution techniques for the algebraic equations. Uh, let's take an example. Uh, uh, Here two are given. This is a very simplistic form of set of algebraic equations, or the system of algebraic equations, where two equations are given. One is the top one. Let me use a pen. One is the first one over here, 3x1 plus 2x2 equals 18, and the other one is minus x1 plus 2x2 equals 2. So this is very simplistic form of uh, algebraic equation, set of algebraic equation. So if we are required to solve this system, we can have a multiple options, and one of them can be uh, a very simple graphical representation, and from the graphical representation we can quickly solve this set. And to do that, what we are required is arbitrarily take one independent and one dependent variable, because whenever we use a graphical representation, uh, it's favorable to have a independent variable along the x-axis and the dependent variable along the y-axis. So if somehow we can translate these two equations into two different functions, uh, and both of the functions depend on a single variable that can be x1 or x2, then we can conveniently translate both of the equations into lines, and we can take the solution from the intersection of the two lines. Since these are linear equations, then definitely they will represent a line with the difference in slope and the difference in the intersection point. So that's one form of solution. This graphical representation is very convenient if we have two equations, uh, but it gets complicated when we have more than two equations, or if we have a set of equations with degree more than one, or non-linear equation, then it becomes complicated. And specifically, if we have more than one, uh, more than two equations, more than two linear equations, or uh, uh, let's say quadratic or cubic equations, are specifically when there is a set of quadratic or cubic polynomials, then getting the solution from the graphical representation is very complicated. And specifically, the reliability of the solution is in question, because for at least quadratic equation, we will have two solutions, and for cubic equation, for three solutions with the single equation. And if there are number of equations, then the solution will be even more. And to get the right intersection point and to describe the solution, it becomes slightly different. Representation, we can feel the solution. We can plot in front of us and can have a clear representation what will be the solution and what will be the significance of that solution. That's the beauty of the graphical representation. And that representation, if we take it beyond graphics, then we can calculate the numbers, but to feel the numbers, what the significance will be, or how those numbers describe the system, it's not as apparent as the graphical representation is. So anyway, this is one form of the solution. We can use the solution if we have a very simple or the set of equation that involves only two equations with two variables. So one thing I would like to remind you, to solve a system of equations, especially linear equations, we'll need as many number of variables are there. So if we have two variables, then we need two equations. If we have, let's say, 10 variables, then we need 10 equations. Otherwise, either will be the system underspecified, or if we have more than equations than number of variables, then it will be overspecified. And in both cases, uh, it will take either assumptions, or we need more representation or more understanding to solve the system. We can have multiple solutions for a system with more number of equations compared to number of variables, or we need assumptions to solve the system if number of variables are uh, more than the available equations. But the graphical representation, sometimes it becomes even difficult to solve the problem, especially if the problem is not properly defined. As three examples are here. One example is the A1. That system does not have any solution, in fact. So it doesn't matter whether you solve it with a graphical technique or you take any other technique, you won't get to any conclusion, because practically there won't be any solution. In fact, this is a single equation, and rest of is product of the equations. But if this is not the not the case, then we can have multiple solutions as well for the same set of linear equation. And this is the case when linear equations in fact overlaps to each other. Then we will have infinite number of solutions if the solution is if the equation is just multiple of the coefficients. So even with this case, this is good to have a good feeling with the graphical representation, but to have a solution, because the problem is already ill-defined, or the system is so ill-defined that it doesn't have a unique solution, or it doesn't have any solution, then we won't get any solution, in fact. And more important is the case where system does have solution, but to get a unique solution from the system, it is difficult, because apparently with the graphical representation, uh, curves overlap at a single point, but they are so close to each other that to get that single point, it is very difficult. For example, with this figure C, I can assume that maybe solution is over here with this x value 1, and this is x2 value. This is just physical understanding, uh, but the solution can be slightly over here. Depend about the resolution of the image from which we'll be getting the solution. So these are three different kind of equations, are the representations by which graphically to get the solution, it's very difficult, or the solution doesn't exist at all, or so many solutions that the system does not define itself. So this is about graphical solution. You can interrupt me at any point if you have any question in between. So either you can post the question in the chat box, or you can turn on your mic and you can have a question. Since we have class of only a couple of guys, so it won't be that messy, I guess so. Another technique is the Cramer's rule. This is also from the elementary school. We have been using it, if I remember correctly, in the elementary level. So that's a Cramer's rule. So a Cramer's rule, it's a relatively simpler form of solution. So it's limited to a simple set of equations as well. So that's a good thing of the solution and the uh, uh, words about the solution as well. So how does this technique works? But before talking about this technique, we have to have another concept that is representing a set of equations into matrix formulation. Let's say we have three algebraic equations, three linear equations, and we want to represent it in the matrix. Then we take one matrix with all the coefficients A, B, and C, another matrix with all the variables X, Y, and Z, and the third one with the constant values. That's on the right side of the equation. So we take all these parameters and clump them into matrix. So if we have this A, B, C matrix, then X, Y, Z matrix, then D1, D2, D3 matrix. If we open up this matrix, then we will again come to the system of equation that is over here. Okay? I guess this is not new, just to remind this concept. So once we have translated this system of equations into the matrix formulation, then computer can help us solve this problem. So because computer can very easily implement the matrix related techniques to solve the system of equations. I guess there won't be any confusion in translating algebraic equations into matrix formulation. So once we have this matrix formulation, the next thing is how Cramer's rule can help us solve this problem. For Cramer's rule, we need one more concept that's a determinant of the matrix. So let's say we have a matrix that involves all the coefficients of three linear algebraic equations, and it is required to get the determinant of the matrix. Then what the determinant is, for 2 by 2 it's very simple. For 3 by 3 matrix it's slightly difficult, and if we get the order of the matrix even higher than 3 by 3, it adds to the complexity of the calculations. But for 3 by 3, even we can manually calculate it very quickly. So what the determinant will be, take the first one parameter of the matrix, eliminate at this moment parameters in the same row and the same column, and take the rest of 2 by 2 matrix. Then uh, once this is done over here, then you can take another parameter that is 1 1 2, leave that row column, the parameters. So first element with the plus sign, second with the minus, third with the plus sign, and fourth with the minus, and so on. This is how we can represent the determinant. And rest is to calculate final number of the determinant. Then that's relatively easier. A11 times cross of A22, A33 minus cross of A23 and A32. So this is one parameter. Similarly calculate the second parameter, similarly third parameter, and at the end with the simplifications you will get a number. So that single number will be the determinant of the whole matrix. And once we have the determinant, the next is how Cramer's will give the solution of x1, x2, x3, all variables. So to take the solution of first variable, what we do need is take the constant values, replace with the first column of the matrix, and leave all the elements of rest of the matrix the same. Then again take the determinant of the matrix. So this determinant divided by the determinant of the original A matrix, that will give the solution of first variable. And you can repeat this technique to get the solution of other variables. For second variable, you will keep all the elements of the first column of the matrix the same, replace second column with the constant values, and column the same, and divide it with the determinant of the original matrix. So this is how you will get second variable value, and similarly the third variable value. And this is uh, a relatively simplistic Cramer's rule technique, and it's easier to implement if we have a set of equations that involves only two equations, or we can have relatively easier if we have three equations, and it gets even difficult to get if we have more number of equations involved in the system. But computer can help us to solve the system. Manually, it will become difficult for higher number of equations, but computer can deal with this. To have a good feeling how computer will work with this, here I pasted a code of MATLAB. I just want to know, आप लोग कितने हैं जो कि MATLAB के साथ familiar हैं या इसको use कर सकते हैं? Can I hear from you? कितने लोग हैं जो कि MATLAB use कर सकते हैं? At least for preliminary purposes.
नो सर
नो सर
नहीं सर नहीं कर सकते
तो अगर लेटर ऑन हमने मैटलैब के साथ सॉल्व करना है इसको, ये तो एक सिंपल प्रॉब्लम है, अगर थोड़े से कॉम्प्लिकेटेड प्रॉब्लम्स आ जाते हैं, सो देयर इज नो सेंस कि हम इस लेवल पे आके मैनुअल कैलकुलेशंस करें. इफ कंप्यूटर कैन हेल्प देन श्योरली वी शुड गो फॉर कंप्यूटर. देन अगर कुछ लोग हैं जो इनको मैटलैब के साथ फेमिलियरिटी नहीं है, आई विल सजेस्ट आप थोड़ा सा टाइम स्पेंड करें, यूट्यूब से ट्यूटोरियल्स देख लें, और मैटलैब की जो बेसिक्स हैं एटलीस्ट बेसिक्स आप लर्न कर लें, क्योंकि इट विल हेल्प इन द अपकमिंग लेक्चर्स. Otherwise, upcoming lectures it will become difficult to solve the problem. And without solving the problem and getting the final solution, it's difficult to get the feel of the technique or the feel of the problem as well. So I suggest आप थोड़ा time spend कर लें. It's not that complicated. At least जो basics है MATLAB की, आप हो सकता है कि अगर एक आर का सेशन देख लें, बिगनर्स का ट्यूटोरियल देख लें, तो आपको बेसिक्स का आइडिया हो जाएगा. सो अगर आप इसी सिस्टम को क्रैमर्स रूल को विद 3 इक्वेशंस अगर आप सॉल्व करना चाहते हैं विद मैटलैब, so you will need only 3 or 4 commands for that. First is define the matrix, then the second step is calculate determinant of the matrix. That's done. Third step is to get all the matrix with determinant of the matrix with replacing corresponding column with the constant numbers. So that's a third term. For example, in the previous slide, if we have to have the solution of x1, then we need a determinant of the matrix with first column replaced by the coefficient with the constant values. Similarly, if we had to have the solution of second variables, then we will replace second column of the determinant of the matrix with the constant, and we will leave the first column and the third column as it is. So this is how we'll take the determinant of the replaced matrix or the modified A matrix, and then we have to divide it with the D. That is the final step. So with these 4 steps, 4 simple commands, MATLAB can get this to the solution very easily. And this is applicable for any number of equations. MATLAB can do it very quickly. I will suggest just go and paste these commands into the MATLAB and just feel how it works. And similarly, you can take several other problems and you can take the same approach to get to the solution. So that's a Cramer's rule. The next technique is again from our elementary school, that's elimination of the unknowns. So if we have a system of equations, then another approach is eliminate one element from the one variable from the one equation, place it to the second equation, and determine the value from the determine the value of second variable from the second equation. And once you value of the second variable, you can place it back to the first equation and get the value of the first variable. So this is again very simple approach that we have to have in the elementary courses. Here it is described in slightly different way. This is the same approach but described in a different way. So what we'll do is, let's say we have two equations with the a11, a12, a21, a22 constant. So I want to make it clear there is a difference between coefficient and the constant values in the algebraic equations. Coefficient is whatever the constant value multiplied with the variable, that's a coefficient. So here we have a11, a12, 21, and 22. These are the coefficients. These are again the numbers. And on the other side, we have a constant value that is not multiplied with any variable. That's a constant value. So whenever we talk about the coefficient, we refer to the specific numbers. And whenever we talk constant values in algebraic equations, that then we need constant numbers that are not multiplied with any variables. So how we will do is we will multiply the coefficient x1 coefficient from the second equation, take that coefficient and multiply with the first equation, and we will get this equation. And the next task is take coefficient from the first equation, x1 coefficient, and multiply with the second equation. So we'll get the second equation over here. So then you can simply subtract second equation from the first equation. So if we subtract a11, a21, x1 minus a21, a11, x1. So if you subtract this, since a11, a21, a21, a11, all these are constant numbers, so it doesn't matter if you multiply in whatever sequence, you will get the same results. So this is cancelled over here. So you will get remaining four terms. And for four terms, you will have only one variable, and you can simplify that one variable to get the solution. So once you have the solution of x2, you can go back and place it in the first equation over here, and you will get the solution of first variable. Or the alternately, you can take this second coefficient, multiply with the first equation, and this coefficient multiply with the second equation, and you will end up with the elimination of x2 and you will get x1. So once you have done all this, only you need is coefficient values for coefficient values and two constants, and you will end up with the results. So that's again very simple approach to solve simple set of equations. But this is very difficult if you have multiple equations with multiple variables. Again, if you have noticed, these values, they are calculated in a very simple way and in the same way as the Cramer rules are. So you can, from the Cramer's rules, you will get the same solution or the same coefficient values as you get from the elimination of unknowns. So you can say that elimination is the basics of Cramer rules. So Cramer rules is derived from this very simple concept of elimination of the variables. So that was the another technique. Another technique is the Gauss elimination. Again, one thing to notice is we have all these techniques to solve again system of algebraic equations. But what kind of technique will be actually using for our purposes? It will depend on the complexity of the system, and second, the accuracy that we desire from the system, and third, the nature of the system itself. So it's possible that sometime the system is so complex that we cannot use graphical technique or variable elimination technique or the Cramer's rule to solve the system. Or sometimes system is uh, as simple as we can get the solution from graphical technique. And another thing is the accuracy of the technique, because all these techniques uh, will be having some accuracy value. So how much we are concerned about, especially it gets very serious when we have repetitive solutions. We have to implement a algorithm in which we have to iterate the solution for a couple of times, and each time the value that we truncate will add to the solution, add to the error of the solution. So there we get in trouble if we don't use the right technique. This gas elimination is another technique. Uh, it works on the same principles as elimination of variables is, but it makes the system or the technique a very, how you can say, uh, a very systematic. So this is a kind of systematic solution of the elimination. The previous elimination is really good when you have to solve the system manually, but if you have so many equations, then to solve them by elimination technique, it is a bit difficult, because you will be using a manual calculations. But the Gauss elimination works on the same principles as the elimination technique is, but it is a very systematic approach, and you can use it for any number of equations. So it does not limit the number of equations. Thus, it does depend on the nature of equation. Sometimes in the elimination, you get denominator as 0, or you don't have anything to multiply, uh, then you get in trouble. Anyway, that's a limitation of the gas elimination. But to learn how this technique works, it's on the same principle of the elimination of unknowns is. So again, for example, here we have a set of equations, and you are desired to develop a solution technique based on Gauss elimination. Again, that's based on the elimination technique. So what you will do is, uh, rather than multiplying coefficient from the second equation, first variable, multiply with the first equation that we have done with the elimination technique in the previous slide. Rather, what you do is take the quotient, let's say the coefficient of first variable of the second equation divided with the first coefficient of the first variable of the first equation. Take this quotient and multiply with the first equation. So when you will do is you will in fact eliminate the coefficient, or you will get the same coefficient as the coefficient of the second equation is. Once you have done this, then the first variable of both of the equation will be the same, and you will simply cancel out by taking the difference or subtracting second equation from the first equation. You will end up with the new equation with one variable less than the previous equations. So if you keep this way, every time you make this calculation, you will get number of variables one less than the previous equation. So at the end, you will only left with the one variable in the last equation. So if you have one equation with one variables, it's nothing more than just dividing the constant value with the coefficient value. You will get the solution. So once you have the last variable from the last equation, you will put it in the previous equation. You will get 2 solution values, and from the two solution values again you get back to the one more previous equation. This is how you back substitute. So in fact, if we summarize this Gauss elimination technique works with two steps. Step one is eliminate the equations, or eliminate the variables and reduce number of variables in each equation. And the second step is back substitute. So by back substitution, each time we'll get one value from the one equation. And then if you back substitute, you will get two variable values from the two equations, one last equation, and other one is the previous equation. So similarly, you will keep on back substitution until you get the solution of all the variables involved. So these are the modified equations. We will solve this one example from the solution to have a good feeling of the solution technique. So once we have all these algebraic equations, these are reduced equations with the Gauss elimination. Again, if you want to have a computer solution, you can make it into matrix and solve the matrix. So that's relatively easier to get the solution from the computer if you have many number of equations with many number of variables. So that's overall concept of the Gauss elimination. To have a good feeling, let's solve this problem. I would say spend some time on this slide and take a good feeling and solve this problem. And then we will continue ahead if we have a good grip on the solution technique, because this solution technique is based for so many elimination techniques or so many solution techniques for the algebraic equations. So that's why we need to have a good feeling and a good understanding of this technique. So I invite spend some time on this slide and then we will continue. Meanwhile, if you have a question, we can discuss the question as well. So let me know if you got it right or you have any confusion with this. I'm online, let me know.
सर ये लास्ट क्वेश्चन का आइडिया सर
ये 9.3.6
यस सर
ऊपर वाले समझ आ गई?
यस ऊपर वाली आ गई सर।
ओके, इसके अलावा किसी और का भी क्वेश्चन है इस पे? ये बाकी लोगों को भी समझ आ रही है?
यस सर।
कोई ऐसा जिसको कंसर्न हो इसमें?
नो सर, ये तो वही पीछे वाले स्टेप्स ही इसमें एक न्यूमेरिकल में सॉल्व किए हुए हैं जस्ट। सिंपल है सर।
सो जो इस पे स्पेसिफिक क्वेश्चन है कि ये लास्ट इक्वेशन की समझ नहीं आई। उससे पहले ये है कि 3.4 जो ये 9.3.4 है, ये इक्वेशन एज इट इज किया जैसे ये 3.1 है, राइट। जो उसके बाद 3.5 इक्वेशन है, ये इनफैक्ट रिड्यूस किया गया है 3.2 को। वो किस तरह से? जो फर्स्ट इक्वेशन है उसका कोएफिशिएंट है, फर्स्ट कोएफिशिएंट 3 और सेकंड इक्वेशन का फर्स्ट कोएफिशिएंट है 0.1। सो व्हाट वी वांट इज कि ये दोनों कोएफिशिएंट्स किसी तरह से सेम हो जाएं। अगर ये दोनों कोएफिशिएंट सेम हो जाएंगे तो सेकंड इक्वेशन को फर्स्ट इक्वेशन में से सब्ट्रैक्ट कर देंगे एंड वी विल गेट अनदर इक्वेशन दैट हैज वेरिएबल लेस देन 3। सो हाउ इट्स डन इज कि ये 3 को एलिमिनेट करके 0.1 के इक्वल बनाने के लिए 0.1 डिवाइड बाय 3 के साथ मल्टीप्लाई कर दें ये फर्स्ट सारी इक्वेशन को। जब फर्स्ट इक्वेशन को इसके साथ मल्टीप्लाई कर देंगे, you will have first coefficient as 0.1 x1, and we have the same coefficient for the second equation. So then subtract second equation from the first one and you will get this solution, right? और अगर हम थर्ड इक्वेशन को भी सेम वे में ट्रीट करें कि ये 0.3 कोएफिशिएंट है, if we want to get 0.3 कोएफिशिएंट फर्स्ट कोएफिशिएंट in the first equation, तो फर्स्ट इक्वेशन को 0.3 डिवाइड बाय 3 के साथ मल्टीप्लाई कर दें। होगा ये कि फर्स्ट कोएफिशिएंट इक्वेशन 1 का वो भी 0.3 होगा और 3 का वो भी 0.3 होगा। सो यू कैन सिंपली सब्ट्रैक्ट 9.3.3 from 9.3.1 and you will get another equation, and that equation is in fact over here 9.3.6. So now we have one equation with with 3 variables and 2 equations with 2 variables. And if we treat the same way कि अगर ये वाले जो कोएफिशिएंट 7 है और यहाँ पे जो दो इक्वेशन दो वेरिएबल वाली इक्वेशन है उसका -0.1900, somehow if we have the same coefficient in both of these equations we can simply eliminate x2 from here. So how we can do that? Divide this 9.3.5 equation with this coefficient divided by 7.033. So this way you will have the coefficient of x2 in this equation the same as you have the coefficient in the last equation. And if you subtract last equation from the previous equation, you will get another equation that has a variable 1 less than these two equations. And you will only left with the x3 from that equation. So that's done over here. You have equation over here. So this 9.3.9 have one variable, 3.8 has two variables, 3.7 has three variables. So then it turns out that ये one equation with one variable है. It's nothing that complicated. Simply divide this constant with this coefficient, you will get variable value. And once you have this variable value, you can place it back to the previous equation जिसमें दो variables हैं. Then you will have solution of two variables, and from that you can get solution of three variables. So that's a back substitution step. And before that, to arrive to this this type of equations, that's a forward elimination by Gauss method. So till here, that's elimination, and from onward you'll get variable values by placing the variable values back into the previous equations. So that's back elimination. So this is how this technique works. If you want to just compare the whether the solution that we got is rightly accurate or not, or to what extent they are accurate, you can place the solutions back into those equations to get the right side of the value or the constant values, and that is compared over here. So these are the solutions from Gauss elimination, and these are the constant values that were already there in the original set of equations. So you can compare these numbers to have a good feeling कि ये कितनी ये कितनी accurate technique है for that this kind of simple problems. So this difference in the solution, if you get to the iterative solution and you have to solve a complex system of equations, or you have to have the solution at each iteration, then this difference will keep on adding, because here we have a third difference at third decimal point in the first result, 7.849. So first number is right, second number is off from the original result, and that's caused by the difference from the third decimal point. So second decimal point or the third decimal point, it will keep on adding the difference around 1% or 0.1% every time. And 0.1% difference, if it's in the system of solutions, or you have millions of iterations or thousands of iterations, then 0.1% in each iteration, it will add up really high in the end result. So that's a limitation of the Gauss elimination technique. So here I have pasted the MATLAB script to solve this technique. You can just copy paste this into the MATLAB and try to solve any system of equations with the linear coefficients or linear variables. So then I advise one homework. Take this problem as assignment and try to solve this. You can use any technique we have out so far, or you can use any other technique that you are familiar with and that's convenient to solve, and get the solution. So what the problem is, we have a cylindrical rod over here, and we have the boundary conditions of the rod. That at the left side of the rod we have a 40 degrees Celsius temperature, and on the right we have 200 degrees Celsius temperature. And because of this temperature difference, heat conducts through this pipe, and the direction will be from higher temperature to the lower temperature. So what we know is only the terminal points, that over here we have 200 degrees Celsius, over here we have 40 degrees Celsius, and we can have the physical or thermophysical properties of the rod. But what's not known is how this temperature distributed within the pipe, whether it varies linearly or there is kind of non-linear relationship inside. And to get that feeling, or to get the knowledge, we have to solve this equation at in-between points. So those in-between points are 1, 2, 3, 4. These are the in-between points. So what is required is calculate the temperature at these 4 points, plot them, and see. Normally conduction is a linear phenomena if the thermal conductivity is constant throughout. But let's see whether this conduction is linear or not. For that we need to solve this system at 4 different points and plot the 4 points and see the slope of the curve. Originally, this conduction follows Fourier's law of heat transfer, and Fourier's law of heat transfer works with the differential equation or the partial differential equations if we have multiple dimensions, not a one-dimensional problem. For at least for this case, because only we have one dimension on the x direction, and for the x direction we can simply use Fourier's law of heat transfer with one dimension. But that one-dimensional problem is in fact a heat equation, and that heat equation is for a steady state case. It works with the second order of the derivative, temperature derivative, with some you can say heat source or difference in temperature. And for steady state problem, this is equal to 0. But the good thing is with second order differential equation, you can use some appropriate technique to reduce it to not differential equation. Those are algebraic equations. And I hope you are aware of the finite difference scheme. with finite different scheme, you can reduce differential equation into algebraic equations, partial differential equations back into differential and back into algebraic equations. And at the end, what we have to solve is only set of linear algebraic equations. And this is done for you. This differential problem is reduced to linear algebraic equations, and where the problem is reduced to only 5 variables from T0 to T4, including boundary conditions. We have 4 in between and 2 at the boundary conditions. These are the boundary, these are already known to us, but in between these 4 temperatures we have to calculate, and the 4 temperatures are given by 4 equations, 1, 2, 3, 4. So at the end, if we solve these 4 simultaneous equations with 4 variables, we'll end up with the temperature distribution inside the cylindrical rod. So that's a work for you. Go back home and spend some time and try to solve this problem and see what is the response of this conduction problem. So that's it. Next time we will move on further with the algebraic equations. We can have a couple of questions if you have any question regarding so far. This is and from my side for today's lecture.
सर अटेंडेंस होगी?
थैंक यू सर.
That's it. कोई इस पे
Yes, sir.
कोई
ये notes
question तो
upload
नहीं?
करते हैं.
हाँ जी, मैं नोट्स अपलोड कर दूंगा और साथ